Okay, so we just found out that we could take lots of samples, and if we do all these samples, even 625 of them, and then we find the mean of all those sample means will equal the population mean. And we saw that the standard deviation would get smaller. So now you're thinking, okay, does that mean I have to do that like every time? Isn't there a shortcut? Well, there is. Let me tell you about it. It's going to be a fantastic shortcut. You're going to love it. All right, so we do have a new notation. Those means of those samples means that we've been playing with. It is the mean of the sample mean. So notice, like the example that we did, we had 25, right? And we found the mean of all those together. So anytime we do the entire set, right, that's all there was. Then we use mu. So mu of x bar will be the mean of the sample mean. So whenever we take the mean of the sample means, that's what we're going to do. And that will always equal the population mean. So, some people ask, and you don't have to really know this, but why do we have to do, like, remember Richard had Richard, I could choose him twice. So the idea is, if we do it without replacement, it would have been very practical, and we wouldn't have duplication. However, we're doing this with replacement, like we put Richard back into the pool of people to pick from again because of two reasons. When we have a small sample, like n equals 2 from a large population, it's not going to make any difference if we have it with or without replacement, right? That's not going to matter. Granted, we had a small population and a small sample, so it did matter, but relatively small samples in a huge population, not going to make a difference. The second thing is, and this is it, we want these ideas of independent events. So it's easier to analyze things, and a lot of our calculations and things that we're going to do in the next few weeks require independent events. That means one sample doesn't really have any effect on the other sample. So we always put back the sample to pick up another sample. Okay, and that's why I say many methods require that simple random sample, which is basically an independent samples. So if you're doing this out in the real world, those voluntary response samples, right, they have a lot of bias. Ooh, so much bias, which means that lots of things could go wrong. It's not really necessarily implicative of the entire population. Implicative, that's such a college word. Anyway, all right, so we want a simple random sample. So basically, we're going to do that repetition. But there is a shortcut, like I said. Actually, there's two cases. If x is normally distributed, so that means the population is normal, right? If the population is already normal, then no matter what we do, our sample is going to be normal. So sample size really doesn't matter. We could have a large population, take a relatively small sample, and if we keep doing that, it's going to be normal as well. It doesn't matter. However, and that's the boring case, so boring, dull, Z's. However, what's the exciting part is when it's not normal. So when we have left skewed or right skewed, or it's all over the place, just crazy multi mode distribution. So if it's not normal, then our sampling, of course, would be not normal if we have a small sample size. But we have this great thing called the central limit theorem, which we will not prove this theorem in this course, but you need to understand what it says. It says, regardless of how that population is distributed, it could be left skewed, it could be right skewed, it could be bumpy all over the place, the sample will be normally distributed if we have a large enough sample. So what's large? That is the key word. Well, let me tell you, don't wait much longer. For us, large is 30 or more. So, and that is a magic word and number in statistics. And again, we're not going to say why it is in this course, but if you are interested, keep on taking stats courses. They're so much fun. It's so interesting. Okay, so 30 or more assures us that we're going to have a normal distribution of the sample mean. So we got to have one of those two cases. So remember, we either have to have that it says it's already normal, or two, we have to have a sample size of 30 or more in order to say that mu of x bar would equal mu. Otherwise, we can't say that, and we'd have to do those samples the long way like we did in the previous section. Okay, we said that mu of x bar equals mu, but remember that the standard deviation was getting smaller and smaller and smaller and smaller and smaller the larger and larger and larger our sample size got? Well, we do have a calculation that basically says that the standard deviation, if again we have those large enough samples or if it's already normally distributed, will be the standard deviation over the square root of n. This is called the standard error. Also, they use that in biology and physics and in the sciences. So anyway, okay, so that is how we calculate our standard deviation. And again, since it's the standard deviation of the x bars, we have that new notation. So just pay attention, and that's what we're going to talk about. That's what we're going to do. The great thing is, again, if it's already normal, no matter how many sample sizes we have, it's going to be basically bell-shaped, approximately bell-shaped. And notice that's the standard deviation. The spread of the data gets smaller and smaller and smaller. Okay, that's normal. Uniform is what we did in the example of the previous video, and that's when it's straight across. Again, at n equals 10, it's almost normal, but at n equals 50, notice how it gets more and more approximately normal. Distribution gets smaller. We can even go to a different shape, the U shape, which is the absolute opposite of the normal distribution. N equals 10, you can see it's not quite normal, but at n equals 50, which is 30 or more, it becomes more and more normal. Okay, so that's what I'm just trying to tell you, that we either have to have a normal distribution or it has to say our sample size is 30 or more in order to say that mu of x bar equals mu and sigma of x bar equals sigma over the square root of n. You need to know those calculations. You have to know them. StatCrunch does not calculate those for you. Okay. So, again, sample size increases, distribution looks more and more normal, standard deviation gets smaller and smaller and smaller. So here we go. A variable of a population has a mean of 35. So this is of our population, so mu is 35. And a standard deviation of 42, so standard deviation of our population is 42. If our variable, so that's talking about the population, is normally distributed, identify the sampling distribution of the sample mean for samples of size 9. So sampling distribution of the sample mean. So that's just asking us, what is mu of x bar? What is sigma of x bar? If we have sample size of 9. All right. So in order to calculate this, in order to be able to do this, our shortcut, we have to have one of two things. We either have to have a normal distribution or a large enough sample size. Notice this says it's normal. It's definitely not large enough sample size, because remember, we have to have n is greater than or equal to 30. 9 is not greater than 30, but it's normal, so that means it's case 1, and we know mu of x bar will equal mu, and sigma of x bar will be sigma over the square root of n. In this case, n is 9. So 42 divided by the square root of 9, 42 divided by 3, because the square root of 9 is 3, that's 14. So that would be our sampling distribution. And we could graph that, right? Because it's normal, the mean would be 35, and we'd add and subtract 9 3 times, and we'd get this nice little curve. Okay, can we answer that same question, sampling distribution? If we don't know the distribution, right? The distribution of the variable under consideration is unknown, so we don't know what's normal now. And we still have size 9. So now it's neither case, right? We have to have normal, which we don't. It's unknown. Or we have to have a large enough sample size. Sample size is only 9. We need 30 or more. So no, not normal. N is not greater than 30. So we can't do it. All right. So this one we had a normal distribution, even though our sample size was small, so we could do it. This one had neither one, so can't do it. Can you answer the same question? Find the sampling distribution. If we don't know the distribution, so again, it's not normal, we have no idea, but the sample size is 36. Now the answer is yes, because our sample size is large enough, even though we don't have a normal distribution, or we don't know what it is. Our sample size is large enough, so we can do that. Mu of x bar would be 35. And sigma of x bar would be 42. My goodness, 42 over the square root of 36. You can't even tell that's a 42, but that's a 42. 42 divided by square root of 36. Square root of 36 is 6. 42 divided by 6 is 7. So you can see our distribution's gotten smaller from a sample size of 9 to a sample size of 36. Went from 14 to 7. All right. Oh, well, that's it, right? That's all there is. Awesome. We got one more thing to talk about. See you soon.